Hello, and welcome back to the course on Physics for Engineers. So we are now on the 8th chapter for this course, which will talk about oscillations and waves. So for the first lesson of this chapter, we will be talking about waves and periodic motion. So what is a wave? So a wave is basically just a disturbance produced by vibration. So a vibration can also be called a periodic motion or an oscillation or basically a back and forth motion. So in this animation here, a pendulum can generate waves such as a swing or a spring oscillating up and down. So both of these cases generate waves because they do back and forth motion. Or basically, if you're just waving your hand. So if you're waving your hand, you're actually doing a back and forth motion. So from the original position to the back to the original position. So that's basically a back and forth motion. So waving basically generates waves. So a wave has a property called a period, denoted by the symbol T. So it's actually a time quantity. It's actually the time for one cycle or one complete vibration or one complete back and forth motion. So the time for that is what we call a cycle. A wave also has a property called frequency F. It's just the number of cycles per second, number of vibrations, complete vibrations per second. And it's basically the inverse of the period, 1 over T. So since the unit of period is time, so seconds, so the unit of frequency is 1 over second or second inverse, and that is the frequency called hertz. So 1 hertz is 1 over second or 1 second inverse. So another property of waves is angular frequency, omega. It's basically just the number of revolutions per second. It's just related to the regular frequency f by a factor of 2 pi. So you have actually encountered angular frequency before when you discussed about rotational dynamics, but in that chapter you called that angular velocity. So it's basically just the same. Angular frequency and angular velocity are basically the same. So let's just focus our discussion on periodic waves, waves that undergo periodic motion. If you have a particle or an object that is going back and forth, it basically generates a wave. So this is an example of the wave pattern that it generates. So this is actually a pattern for the displacement of the object. So the dots that you see here represents the location of the center of the object. And the center of the object is actually waving. So there is a maximum and minimum displacement of the center of the object. And that maximum and minimum displacement is associated with the property of the wave called the amplitude, or denoted by the symbol A. So it denotes the maximum displacement of the particle from the equilibrium position. So in this case, from the equilibrium position, which is 0, it goes to a maximum point or maximum position, A, and to a minimum position, negative A. And A is what we call the amplitude, the maximum displacement from the equilibrium position. So you will also notice that the waves have maximum points here that are repeating, and these are what we call the crests of the wave. So this is a crest, this is a crest, this is another crest. And the lower points, the points of minimum displacement, are called troughs. This is a trough, this is a trough, and this is another trough. So the distance between crests or troughs is called the wavelength. So that's basically how you measure the length of the wave. The distance between two crests or two troughs. So as I've mentioned before, the time for one cycle one complete vibration is what we call the period, T. So the time that the pattern repeats from crest to another crest, that's what we call the period. The time for one complete cycle or one complete vibration or one complete back and forth motion. So from crest to another crest, or basically the time for one wavelength, that is the period. So the wavelength, the frequency, the period, and the speed of the wave. So you will notice that the wave is actually moving to the right in this case. The speed of that wave is given by this periodic wave equation. So the periodic wave equation is applicable to all waves, all types of waves, and it relates the wave speed, the wavelength, and the frequency or the period of the wave. So for this chapter, we will only focus on mechanical waves, but there are other types of waves that are non-mechanical in nature. So mechanical waves are disturbance produced by mechanical vibration, and they need a medium such as a solid, liquid, or gas in order to travel or propagate. So unlike non-mechanical waves such as gravitational waves or electromagnetic waves is light. We will discuss actually this on the last chapter for this course. Those types of waves actually don't need a solid, liquid, or gas in order to travel. So only mechanical waves need a medium. So all waves can also be classified into two types, depending on the direction of the particles moving and the direction of the propagation of the wave. So a transverse wave is a wave wherein the direction of motion of the wave is perpendicular to the motion of particles. The example of these are waves on a string. If you jiggle a string up and down, so the particles of the strings are moving up and down, you will see a wave that's moving to the left or to the right. So it's perpendicular. Electromagnetic waves or light are also transverse waves. So a longitudinal wave is a wave wherein the direction of the motion of the particles are parallel to the direction of the motion of the or velocity of the wave. So example of this is spring waves, waves generated by springs, sound waves. We will discuss this further in the next topics, sound waves and gravitational waves. So this is an example of the comparison of a transverse wave and a longitudinal wave as illustrated by a spring. So if you jiggle a spring up and down, you will create a wave that moves to the left or to the right. So the motion of the particles of the spring, in this case, is perpendicular to the motion of the or velocity of the wave. So that's a transverse wave. A longitudinal wave, on the other hand, is if you jiggle the spring left or right, you will create a wave that is also moving to the left or right. So the motion of the particles of the spring is parallel to the direction of the motion of the wave. So that is what we call a longitudinal wave. So sound waves, gravitational waves are examples of longitudinal waves. But again, electromagnetic waves and gravitational waves are not mechanical waves. And in this chapter, we'll only focus mostly on mechanical waves. You will discuss electromagnetic waves on the last chapter of this course, but for this course, gravitational waves will not be discussed. Okay, let's now have an example. So let's try to find how the waves or the vibrations produced by a wall clock. So a wall clock has three hands. You have the hour hand, this one, the minute hand, the longer one, and this red one here is the second hand for the seconds. So hours, hour, minute, seconds. So for a wall clock, find the frequency of letter A, the hour hand, letter B, the minute hand, and letter C, the second hand. So once you know the period, if you know the period for each of the hands, you can solve for the frequency, since in this problem, you need to solve for the period and the frequency. So once you know the period, you can solve for the frequency by taking the inverse of the period. So let's start with the hour hand, letter A. So the period for the hour hand is 12 hours. So this hour hand here goes back to its original position in 12 hours, or makes one revolution or makes one cycle in 12 hours. That's the cycle of the hour hand. So 12 hours is 43,200 seconds. So if you take the inverse of that to get the frequency, so 1 over 43,200 or 1 over 12 hours is 0.000231 hertz. So that's actually a very small frequency. So this means that it doesn't happen that much. So it's not frequent. So it only happens once every 12 hours or once every 43,200 seconds. That's what this frequency means. So let's now go to the minute hand. So the period for the minute hand, the time that it makes one complete revolution or one complete cycle in the wall clock, is 1 hour or 60 minutes or 3,600 seconds. So if you take the inverse of that to get the frequency, 1 over 3,600 seconds is 0.000278 hertz. So in layman's term, the frequency of the minute hand is once every hour or once every 60 minutes or once every 3,600 seconds. Okay. So for the second hand, the period is 60 seconds. So this, the fastest hand in all of the three hands of the clock is the second hand. It will make a complete cycle in 60 seconds. So the frequency is 1 over 60 seconds or 0.0167 hertz. Okay. So let's now go to another example. So this is the vibration of a light bulb. So the light from an incandescent light bulb, so the yellowish light bulbs, the old light bulbs, not the LED types, it's actually flickering at a rate of 60 hertz. So it's actually shining and then dimming, shining and dimming at a rate of 60 hertz, meaning 60 flickering in 1 second. That's what's the rate of 60 hertz mean. 60 times, 60 cycles, 60 flickerings in 1 second. So we are now asked to, we're now asked how fast in time is 1 flicker. So 1 flicker is 1 cycle. Time for 1 cycle is basically period. We are asked for the period of this flickering. So since the frequency is inverse of the period, then the period is inverse of the frequency. So we already know the frequency is 60 hertz. So 1 over 60 hertz is 0.017167 seconds. So this is actually a very fast time, 16.7 milliseconds. It's actually too fast for our eyes to detect. So what we actually see is just a continuous shining of the light bulb, but we don't actually see it flickering. But there are times that we see it flicker when the frequency actually decreases. So when the frequency actually decreases to 10 hertz, so maybe you will notice the flickering. But 60 hertz cannot be detected by our eyes, actually. Okay. Another example is ocean waves. So an ocean wave is actually a surface wave. It's actually a combination of longitudinal and transverse waves. So a fisherman notices that this boat is moving up and down due to ocean waves. He notices that the distance between two wave crests is 100 meters, and that his boat moves from the highest to the lowest point after 1.5 seconds. So what is the frequency and speed of the ocean wave? So in this problem, we are given the wavelength, the distance between two wave crests. It's 100 meters. So that's the wavelength. But this time given here, 1.5 seconds, this is just the time from the highest point, so from the crest, to the lowest point, which is the trough. So the time for that is 1.5 seconds. And that's actually half cycles, because the full cycle is returning to crest. So from crest to another crest. So we're only given half the time, half the period, 1.5 seconds. So we need that to multiply by, we need to multiply that by 2 to get the period, which is 3 seconds in this case. Okay. So the frequency is 1 over the period, 1 over 3 seconds, and we get 0.333 hertz, or 1/3 hertz. So for the velocity is from the periodic wave equation is just the wavelength times the frequency. But we know that the frequency is 1 over the period, so you replace this by 1 over t and you get lambda over t. So this is another form of the periodic equation in terms of the wavelength and the period. And we get 100 meters over 3 seconds, or 33.333 meters per second. So you will notice that I didn't use the frequency here that I obtained. Actually, you will still get the same answer, but it's much safer to use lambda over t here, the original given values, because if you made an error in your calculation of the frequency, then your velocity will also be affected. So as a general rule, always use formulas that utilize the given values and not the calculated values. Okay, so that is it for this example. So for our last example, we'll consider radio waves. And again, radio waves are not mechanical waves. They're actually electromagnetic waves. So sample of radio waves are Bluetooth and Wi-Fi are radio waves. And they are the same waves generated by your radio stations. So in this example, you have radio waves. And since they are basically light that you cannot see, they are invisible light, they still have the same speed as the speed of light, which is 3 times 10 to the 8 meters per second. So find the wavelength of radio waves generated by an AM radio station with frequency of 540 kilohertz and an FM radio station with frequency of 104.5 megahertz. Okay, so from the periodic wave equation, the wavelength is just the velocity over the frequency. So here we are given with the velocity, and we are also given with the frequency. For the AM radio station, 540 kilohertz. For the FM radio stations, 104.5 megahertz. So the names or the numbers associated with your with our radio stations are actually their frequencies. So for example, Love Radio 95.1. That's actually 95.1 megahertz. So for letter A, an AM radio station, the wavelength would be the speed over the frequency, which is 540 kilohertz. Kilo means times 10 to the 3 or 1 times 1000. And you will get 555.56 meters. So this is actually a very long wavelength. 500 meters much taller, very much taller than buildings. It's actually as tall as mountains. 556 meters, 500 meters is actually as tall as mountains. So the wavelength of AM radio waves are comparable to the height of mountains. So for letter B, frequency, the wavelength for an FM radio station with a frequency of 104.5 megahertz. Mega means times 10 to the 6. You multiply by 10 to the 6 or 1 million. And you will get 2.87 meters. So the wavelength of AM radio waves are actually very much longer as compared to FM radio waves. But again, they are electromagnetic waves. Okay. So that is the last example for this lesson, and that ends the lesson on waves and periodic motion. So I will see you again on the next lesson, which is all about simple harmonic motion. So bye for now.